Alright. Alright, hi everyone. We're the cargo plane group. We consist about 10 members or 11 members. Some are volunteers, most of them are enrolled in the class. Our advisor is Professor John LaRue. Alright, so a little background on our project. So our project is to design a heavy lift RC airplane for the SAE competition. And the SAE competition is on April 24th. It's about 75 teams, and then so the goal of the competition is pretty much just to design an airplane within the SAE restraints to lift as much payload as possible. And so our particular goal is to try to get a payload up to around 30 pounds while keeping our aircraft below 15 pounds. So some of the bigger constraints for the competition that really shape our design is the first one is the total height, width, and length of the plane has to be less than 175 inches. We can't have no fiber reinforced materials in our plane, and to keep the playing field of competition level, so one team can't go out and just buy the best motor so they get the most power. They have a requirement. We have to have a power limiter that reduces our power to 1,000 watts, and also our payload. The dimension of our payload bay has to be 4 by 4 by 10 inches. Our team organization is broken down into to the different subsystems. So we have the fuselage, the wing, and the curb section for our plane, the tail, controls and electronics, motor, and landing gear. Our budget was broken down into 4 different categories, mainly. A big chunk of our budget is going to be going towards the registration for the SAE competition, which is about $700. Then a big chunk of our budget is for the electronics. We were able to save a little bit of money on electronics just by recycling some of the parts from the old plane from last year. And then a good amount of money goes into the materials. We have to purchase a lot of wood. The balsa wood could get pretty expensive, and then we want a little bit extra for if pieces break and stuff. And then just different equipment to the sealing iron and the blow dryer for the monocoat, X-Acto knives to make cuts in the wood and stuff.
All right, sorry. So part of our design process is we have to allocate certain dimensions to each, or a certain amount of footage to each dimension, with a primary focus on wing length. Currently, right now, we have about 90 inches of wing length that we distribute, and it's distributed over a upper and lower lifting surface. So we have much maximize our lifting surface with the length constraints. Each opponent, and then each sub team is essentially divided into, or each team has a length that they're allotted to, and I believe the dimensions are 90 inches to the wing, 36 inches to the total length of the fuselage, and about 16 to the total height right now. The way the plane is looking, we have about currently a foot extra of extra length that we're going to, looks like we're going to end up allocating to more rudder surface for stability and a little more length for additional lift. Currently, we also have a big focus on part integration to really help with the ease of manufacturing. Because last year's cargo plane had an issue where, while parts were feasible in some sort of AutoCAD programming, they weren't necessarily viable when they would come together and teams would meet. We have a lot of new components from last year's plane. We have gurney flaps, which unfortunately you can't see. We have joined the wingtip together to help reduce, essentially induce drags that will occur due to vorticity around the wingtips. We have a tri-rudder system now to give us additional control surface for our pitch. we have a positive stagger. It's a little difficult to see in this picture here, but we actually have a positive stagger between the upper and lower wings. What is it? We have slotted flap. We also have slotted flaps along the lifting surface to help increase the total overall lift we can carry. We also have an improved aerodynamic profile to help reduce the drag that the plane sees.
Yeah, the reason why we do the biplane design is because we have a limited dimension restriction. And in order for us to lift as much cargo as possible, we're trying to maximize the wing area. And in order to do that, biplane will be an ideal option. And we looked into a couple of research for the biplane design, and we know that positive stagger will increase the lift coefficient, and then that's the reason why we do positive stagger. And as for the wingtip design, the joint wingtip, last year we did that, but we didn't know why, because there were not a lot of research on that topic. The reason for that is because in real life, such a construction is not really feasible. It only can apply to UAV or like smaller scale aircraft. And this year, in order for us to investigate the effect on the wingtip structure, we actually rebuilt around 10 models for a wingtip, and to see how we can optimize the structure. And as you see, this is the one with no wingtips, and there are a lot of turbulence generated at the wingtip. And with the optimal design, we're able to minimize that to that. And all the fluid dynamics simulation was done by SolidWorks, and we will use COMSOL to confirm the results in the future. We also did FEA simulation with SolidWorks. We built a service model, a full-scale service model for stress analysis, as well as fatigue and drop test analysis.
So in a heavy lifting competition, one of the big goals is to increase lift. The more lift, the more you can carry. And two ways that we're looking to do this, we have two major lift enhancing devices, is the gurney flap, which Dylan mentioned. And what that is a small 90-degree protrusion from the trailing edge, usually about 1% of the wing port. And what that does is, as airflow goes to the trailing edge, it increases pressure on the high pressure side and actually decreases pressure on the suction side. What this does is it helps reduce the adverse pressure gradient as the flow is moving towards the trailing edge, and that's going to help prevent separation, which would drastically reduce our lift. Separation is a big problem for us. We are using a very high lift, high camber airfoil. And in high cambered airfoils, you have stronger adverse pressure gradients. So this is an attempt to combat that and help prevent stall. The other, and that is the picture of the gurney flap and how it does that. The other device that we are looking into is a slotted flap design in comparison to a traditional plain flap design. The plain flap just hinges down, as you would imagine. The slotted flap actually creates a bit of a gap, and what this allows is for airflow on the high pressure side to spill over onto the top of the flap and help prevent separation by giving additional momentum to the boundary layer on the top surface. And in the graphs up to the left, you can actually see that the slotted flap versus the plain flap, it not only increases the coefficient of lift in that section by a significant margin from 2.3 to 2.5, but it also increases the maximum stalling. So as far as construction methods, last year was our first year being active in some time, and it was very much an experimental year in how to construct things. This is the wrap section that we built from last year, and as you can see, there is a very large horizontal stagger between the upper and lower wings. This year we brought the stagger much closer together into a biplane design as opposed to a joined wing and tail. This is going to make building the wrap in particular much easier, as the main spar is going to be significantly shorter and with less compound curves, as well as for stringing and coating. Another major design iteration from last year to this year is how the ribs are placed. There are going to be slots that actually protrude up from the main spar of the wing, and that is going to help us slide the ribs exactly into place as opposed to sliding them down the length of the spar, and then roughly measuring where we need the ribs to be. The spar for the curved section will be 3D printed as it was last year. However, with the simpler shape, it'll be much easier to put together and slot the transitional airfoils onto. Another big change for us is in the leading edge, which unfortunately you can't see in that one. Black Monaco was on sale. We used that instead of the translucent. But we have a series of stringers that coat over a recessed area on the leading edge, and that proved to be rather difficult, especially in getting a smooth shape. So this year what we decided to do is we're going to make a negative mold of our leading edge, and then coat it with sandpaper, and then just run that down a single block of balsa wood, which is then going to be applied to the leading edge in that negative space there. And Chris, if you
okay, and then so currently where we're at in our project, we are completed with the design process. We have a full CAD model. So currently we're in the fabrication phase. So right now we've just been laser cutting all the individual components, and we're starting to assemble all the components. And our plans for the future, we want to be completed with fabrication about March 20th. Around March 20th, which would give us about a month before the competition to do flight testing. And we want to be done with the flight testing with our plane running fully and being completely optimal by about a week before the competition. And then the competition lies on April 22nd. That completes our review.